Hello everyone, welcome back to the channel. Today we are going to be talking about distributed consensus. Now this is only consensus in the computer term. If I could actually solve consensus, my parents wouldn't be divorced. But nonetheless, here we are today. So let's get into some content because I have to leave the house soon. Alright, so as I previously mentioned in the last video, the entire point of doing all of this is to basically build linearizable storage. And what linearizable storage is going to allow us to do is build applications on top of that, such as distributed locking or service discovery mechanisms. Obviously, we'll cover those in a later video. So the algorithm I'm actually going to be talking about today is called Raft. And what Raft allows us to do is build a distributed log. Why do we want a distributed log? Because logs are ordered, hence they are linearizable. And that is extremely important for us. So how does Raft actually work? And I guess additionally, why am I not talking about Paxos or some other distributed consensus algorithm? Well, Raft is just a little bit simpler to teach, hence why it's popular, and easier to understand. So doesn't that work out for all of us bozos? Okay, so how does Raft actually work from just like a very high level perspective? Again, we're building a distributed log. And what the log actually contains is we have an operation and we have something called a term number. And we'll touch into what the term number really signifies and what it means a little bit later in this video. But the gist is that we're going to have a leader, and the leader is asynchronously replicating over to the follower nodes. And keep in mind that this is asynchronous replication, so it is possible for one follower to be behind. As you can see, this log is not as up to date as the one on the leader. It's not possible for all of the logs to be behind, as we'll talk about probably mostly in the next video. But yeah, for this video mainly I want to focus on one of two steps of Raft, which is actually picking which node is going to be the leader, because that in and of itself is quite an interesting process, and in picking the leader we can kind of ensure a bunch of invariants about our system that are going to be important when it comes time to actually start making writes. So let's look at Raft leader election and how does it work. So basically our Raft leader, which we can see right here on the left of the screen, has something called an epoch number. And in addition to that, we'll touch more upon what this epoch number actually means, but as a result of just kind of how Raft works, we're going to be constantly sending heartbeats or pings over to our followers on some interval. And basically, eventually, if this guy decides to go down, one of our followers is going to say, hey, I haven't received heartbeats anymore, it's time for me to complain. Obviously, we don't want them all complaining at the same time because then it's just going to be bad for our system. We're going to have a lot of network traffic, a bunch of other stuff. So let's say, we randomize the amount of time it takes for each follower to complain. This guy will complain after 10 seconds. This guy will complain after 5 seconds. So obviously, because the bottom node is going to complain sooner than the top one, it is going to be the one that ultimately proposes a new election. It's going to say, hey, I haven't heard from the leader in a little bit, so let's start a new election, and what about me as the candidate? So what this guy is known as is the candidate, and as you can see, because the epoch number before of the previous leader was 28, this guy is going to say, okay, well, I am candidate for term 29. And so that is going to be how the election actually gets started. So what happens during the election? Let's scroll on to our next screen here. This one has a lot going on, so I'm going to try and show it all properly. So there are a few actual possibilities of things that can happen, and I'm going to show them all off. So let's say this is the candidate right here over on the top left. So the candidate is now going to propose a term number 29, and let's say it's got a log like so where it has two operations and you can see the epochs that those operations were written from. So let's say the message actually gets to the previous leader, right? If the previous leader receives a message from a potential candidate saying, hey, you're no longer the leader, well, then the only thing that leader can do is say, shoot, I guess I'm no longer the leader. So it's going to change its status to a follower for term 29. Another possibility of what's going to happen is that the node that receives this kind of proposal is just going to be a follower from a previous epoch. And what that's now going to do is, even still, as long as basically the term number is going to be lower than the one being proposed, it's going to increment its local term number to the term number of the proposal. Even still, it doesn't necessarily have to vote for the candidate yet, but it does need to increment its number to that term, and we'll see why. And then next, another possibility is that we go to a node with a higher term number, a greater than or equal to term number than the one being proposed. So in this case, it's a follower from term 29. That implies that there was already a leader for term 29. And if there was already a leader for term 29, then we are going to go ahead and say no to our candidate over here. So that is why we have this no operation over here. As you can see, we've already processed a write during this term. And then finally, another possibility is that we reach out to a follower from term 28, and the follower is going to say, oh, okay, well, I can see there's a new election going on. Let me change my term number to term 29. And because your log, here's the follower log right down here, here is the candidate log. Because the candidate log is greater than or equal to as updated as my local log, I am going to respond yes. And it's very simple, basically. If you have a term number that was equal to the term number being proposed, or rather, if you have a term number that was lower locally than the one being proposed, and the log that you have locally is either the same as the one being proposed or it is less up to date, then you can go ahead and say, I will give you my vote. Otherwise, you will not give them your vote, but you will still, of course, update your term number to the one being proposed if it's higher than your local term number. So a lot of steps, yeah, but hopefully that generally makes sense. Okay, so what actually happens when the candidate receives some votes? Well, if they hear yes from a quorum, keep in mind from our leaderless replication videos, that means a majority of nodes, it has won the election and it can be a leader. So why does this system actually work for, kind of ensuring the integrity of our logs such that we can make sure that we only have one leader at once? Well, for starters, we obviously cannot elect two leaders at the same time because of quorums. If we have three nodes, say I get these two votes, I can't also get these two votes because there's overlap between them. So a quorum is not going to solve our issues there. In addition, for number two, old leaders cannot come back due to this fencing token / epoch number. What is a fencing token? Well, the fact that we have this epoch number basically means that if an older leader proposes a right with a lower epoch number than the current term, we know that it is an old leader and it shouldn't be proposing rights, and then we can say, I'm not going to accept this. That's called a fencing token. That is a term used in distributed systems where basically you assign a number to the current leader, and that way if an older leader tries to do something, you can say, well, it's got a lower fencing token, I don't care about this. And then finally, the leader has an up-to-date log and it can backfill stale nodes. So if you have a node that basically is not completely up-to-date in its log and the current leader goes down, so it's not able to basically fill it up, you know that the new leader is going to take over and have an up-to-date log, and that way it can actually go ahead and kind of get the other nodes up to speed, which is a good thing. If it is completely possible that you would have another node basically that is more up-to-date than the leader. However, if that node is more up-to-date than the leader, it means that that right must not have gone to a majority of the nodes, because if it had gone to a majority of nodes, then the leader could not have been elected in the first place. Recall that the leader's log needs to be more up-to-date or equal to a majority of nodes. So any right that is basically more up-to-date than the leader can't be on a majority of nodes. Hopefully that makes sense. Not that important for the proof, but interesting stuff nonetheless. So again, this is a pretty short video because mainly I want to cover these two fundamental steps of Raft, where the first one is leader election. The second one, of course, is where once we have a leader, we actually start broadcasting some rights. And that's not too complicated either, but I think that it makes a lot of sense in order to kind of break these down into manageable chunks, because there is a lot of thinking to be done to kind of wrap your head around these topics and why they actually work and achieve consensus. So guys, I hope you enjoyed the video. Talk to you in the next one, and have a good rest of the weekend.